Hello, welcome back. In this lecture, sorry, I'm still flexing all my newfound capabilities here. We're going to be talking about shaft design. So, in our last lecture, we talked about different ways of assembling a shaft. In this lecture, we're going to go ahead and take what we know and we'll talk through a design problem for a shaft. Now, one of the reasons why I'm giving you this lecture right now is because I did cancel our in-class lecture sessions this week, and that's because I have a meeting on Friday that's going to last all morning, so I will not be able to be in class that day. So I figured it'd kind of be unfair to show up for one class, not for the other class, and yeah, so that happened. In any case, this is going to be really important for you because you have a homework problem next week that's going to be a design problem. Okay, for a lot of what we're going to be doing moving forward is I'm going to be giving you design problems on shafts or on choosing components or really on a lot of different kind of design type of problems. And for that purpose, I think it's really good to walk through the design process for each of these components. The design process for everything is pretty much the same. First of all, you understand what failure conditions exist, and then you move from there. The design process that we've talked about since freshman year, it is still valid. We will talk about that a little bit later date, because right now we're focusing on just designing components. But in any case, we're going to design a shaft component today. So, doop-a-doo. With shaft design, we have a number of conditions that we have to take care of. So let's say in order to design a shaft, the very first step you need to know is, what does the shaft do? If it's transmitting torque, which it usually is, then the shaft that we're going to end up designing is probably going to have to be pretty beefy. So what I'm going to go ahead and say is this is going to be carrying torque between two pinions. And we'll say it's a torque of, maybe it's got to carry, I don't know, 3,000 pound-inch torque. Okay, between two pinions. And we'll say the pinions, just in order for our machine spacing to be proper, we're going to say that the pinions have to be 3 inches apart on center. Okay. I am not using the right word here. It's not a pinion. It's a gear and pulley. It's a pulley. My apologies. I'm getting my P words mixed up. So that happened. Okay. So here's what we need it to do. Okay. Now in best practice, you generally only have 2 bearings for an entire shaft. We talked a little bit about over-constraining or under-constraining systems. The issue with having more than 2 bearings on a shaft is that it does tend to be much more over-constrained. If you have really, really long shafts, then you could consider having 3, but having 2, it allows for flexure of the system. Flexure of the system usually just means the bearings rotate inward a little bit. You don't have issues with residual X stresses or axial stresses. So that's kind of it. So once we understand what it's going to do, now we need to know, okay, since it's got pulleys, it's going to be rotating, it's carrying torque, we need to know now our assumptions and really our conditions. First of all, we're going to have to design for fatigue. Why are we designing for fatigue? Well, because it's rotating. If it's rotating at all, that means every time it rotates one rotation, it's going to experience a cycle. Okay, so we're going to have to figure out what the fatigue loading is. Beyond this, we know it's not just going to be carrying torque, but it's also going to have a moment load, and it's going to have a shear load. Okay, so we'll have three different stresses present for this. And we have to consider it in fatigue. And really, we don't have any other conditions for what the shaft has to be. Now, what the book suggests for shaft design, and by the way, I forgot to give you a reading assignment this week, so your shaft reading assignment will be due next week with the reading assignment for the following week, so you'll have 2 reading assignments next week. Just FYI. But when you have that, when you have the reading assignment, the book suggests that don't design a brand new shaft. Use an existing shaft or redesign an existing shaft. Don't try to build something brand new. Just because this process can be a little arduous. We have talked in this class a lot about stress analysis and fatigue analysis and all of those fun things. In practice, people don't really want to have to go through the math to figure that out. Okay? So, what are we going to do for this design condition? Well, the next thing we need to do is do our axial layout. How is our shaft going to look horizontally? Okay, we know we need to have these 2 pulleys be 3 inches apart, just as per the design conditions. This may be because of geometries of the machine that it has. One belt has to face one way, the other belt has to face another way, that kind of a thing. But in any case, we know that we've got 1 pulley here, and we've got 1 pulley over here. And this pulley, regardless of the diameter, regardless of what it is going to be transmitting 3,000 pound-inches of torque. Okay? Because maybe this is what's being output from one motor, and we're just gearing it down to this pulley or whatever. And let's say this is going to be at a pulley diameter of 4-inch diameter. Okay? And we have to transmit this 3,000 pound-inch torque to another pulley where this distance here is 3 inches. Okay? Now, with this axial layout, we got to figure out where our components are. How are our components going to stay in place? Well, if I make this a stepped shaft, then these pulleys are going to butt up against that step on that shaft, and that's going to hold them in place axially. Okay, we'll say I'm going to use a clip ring right here. It'll just clip on to the shaft right here. And then right away we will have, oh, actually, you know what? No, I don't want to do that. I'm going to put a little bit of a spacer, just a bushing. So this is my bushing. And then I'm going to put the bearing just right away. Okay, so at this point we have pulley, bushing, bearing. This bushing is going to be 1/2 inch. Just because it'll give a little bit of play between the pulley and the bearing, and it'll prevent them from running into each other, causing problems that way. Okay. What happens to the shaft outside of these, we don't really care about. You can make it longer if need be. You probably want to make it a little bit longer than the bearing on both sides. So maybe we'll add 1/2 inch shaft on both sides. Okay. So the overall layout, if I was going to design this and just start labeling it, is I'm going to say this diameter doesn't matter, but it's 1/2 inch, and then we have bearing, and this bearing will say maybe this bearing takes 3/4 of an inch, and then we got a bushing. The bushing goes right over the shaft, and we'll say that this is a 1/2 inch. And then we got our pulley, and we'll say our pulley is also a 1/2 inch. Pulleys don't tend to be very, very wide. Then we got our step shaft here. Let's see, this is going to be a 1/4 inch, 1/4 inch. So this here, the step shaft is going to be 2.5 inches. Then we got another pulley over here. It's also a 1/2 inch. We got a bushing, also 1/2 inch. We got our bearing. Bearing is 3/4 inch, and then we got 1/2 inch of shaft outside of that. Okay, so I haven't done any real math yet. I'm just looking at components and saying here's how wide they are. From this, I am designing an axle that's oh man, I'm gonna have to do head maths now. Dang it. This is 1.5 inch plus 3/4 inch is 2.25 inch. 1/2 of this is 1.25 inch, so 2.25 plus 1.25 is 3.5. 3.5 multiplied by 2 is this is a 7-inch shaft. Okay. So I now know the length of the shaft that I'm going to be designing. Sweet. If 7 inches fits nicely, we're in good place. If it doesn't fit nicely, I may need to reconfigure this. I may need to change my design to make sure that my pulleys are closer together. Another thing that I can do to reduce the length of this shaft is I could put the bearings on the inside. Now, putting the bearings on the inside does mean you have a cantilever load on these pulleys, and it also does require a little bit of finesse when you assemble this. You basically have to mount this directly to your component before you try to assemble it. Regardless, that could be an option if your shaft is too long. If it can't be 7 inches, you can put the bearings on the inside. For this case, I'm going to put the bearings on the outside because I like having distance between my bearings. Having the distance allows it to carry a moment load better. It also allows it to take a shock load better. So I'm going to leave my bearings on the outside. Putting the bearings on the inside is not always a bad idea. Okay. All right. So got my shaft configuration now. I got my axial layout. We're good. So what's the next step after axial layout? Now that we know that this is a 7-inch shaft, what's the next step? Well, now we need to actually draw a free body diagram of the system. Okay, so with this, I'm going to go ahead and take off the bushing. All the bushing does is it acts as a boundary condition that if any lateral loads exist on the pulleys, that those pulleys will not move relative to the bearing. So that's kind of it. We're going to assume that the bearing uses a set screw, and by doing so, that means that you can exert lateral loads on the bearing directly, and it's not going to move. We'll assume that it uses a set screw on both sides, so that will handle any lateral loading. Okay, so just drawing this, I'm going to go ahead and remove the bushing, I'm going to replace the bearing with a load. I'm going to replace the pulley with a load, both of the pulleys, and also the other bearing. So I got this, goes up, you got step shaft in the middle, like this, and that's 7 inches, okay? And we know that 1 inch and 3/8 of an inch, that's 7/8 of an inch from the end. We have our RB load. Now our RB load, if we look at it from the side, RB doesn't have to be only in the X or Y direction. It may have, if this is here, let's say X is along the direction of the shaft, this is Y, this is Y and Z. This right here is RBY. This right here is just general RB, and then you have the RBY component of that and your RBZ component of that. So your bearings will exert a load on your shaft to ensure that the shaft doesn't move. Okay. Now what we'll say here is for a pulley, if we were to draw sideways on the pulley has a belt that goes onto it like this. That belt is constantly in tension. Okay, a belt can't exert a compressive load on a pulley. Now we haven't started talking about pulley design yet, so I'm just going to kind of give you the loads on those pulleys, and we'll get to pulley design later. So for a 4-inch diameter shaft, we're going to assume that this bottom tension, when fully loaded, is 0 pounds. That's actually not true. There is some tension. There is going to be some load on the bottom. I guess, you know what? We'll go ahead and say that maybe it's got a 100-pound tension load on the bottom. Okay, and then we'll go up here and we'll say, okay, in order for this to have 3,000 pound-inches of torque, that means this is going to have to be 1,600 pounds being carried by one side. That's going to give a net total between these two forces of 1,500 pounds. 1,500 pound inches at 2 inches away from the center of the pulley, which means that is 3,000 pound inches, which is a whole lot of torque. Usually you do not use pulleys for transmitting that kind of torque because it's just a ridiculous amount of torque. Pulleys are generally used for smaller force values, but we'll ignore that for right now. Okay, so this is what one pulley is going to look like. It's got a total shear force of 1,700 pound force, and we'll go ahead and say that 1,700 pound force is exerted entirely in the Y direction. Okay, so this is F pulley 1. 1,700 pounds in this. We're also going to apply a torque. It's going in this direction, so it's going to be going this way. So we will have a torque applied this way, TP, and TP is equal to 3,000 pound inches, which is what we designed earlier. Okay, cool. Now, maybe when you design pulleys, oftentimes what you use them for is you can use them to transfer forces out of plane. You can use them to transfer force directionality, that kind of thing. But usually what you do is you use them to exchange power, where you're either increasing the torque and decreasing the speed, or you're increasing the speed and decreasing the torque. What we're going to do here is okay, so when I say that, the force being carried through this line is 1,500 pounds being actually transmitted here through this pulley system. We're going to want to step that down to only 1,000 pounds. Okay, so we'll say this one is being stepped down to 1,000 pounds. Now when we draw this pulley, it's got 1,000 pounds difference between the two. We'll say that this pulley has a 100-pound preload, which means we're dealing with 1,100 pounds and 100 pounds, which again is really, really large for a pulley. Doesn't matter. We're just figuring that out anyways, okay? And in order to get 3,000 pound-inches out of this, we're going to have a 6-inch diameter pulley. So this one's 6-inch diameter. It's going to also exert that same TP, which is the torque from the pulleys. But here, now this one, maybe we say it goes in the same direction. This one is going to be 1,200 pounds, because that's 100 plus 1,200. And this is equal to FP2. Okay, so now just configuring the forces, figuring out what the forces are on here. Now we've also got RB2Y. This is RB1Y. I'm not going to create a force in the Z direction. We've done some examples where we've had to do that. And you can go ahead and do that, but if your pulleys are offset, you will have to do that. Otherwise, you can design as long as your pulleys are in the same direction, the forces are in the same direction, in the same plane, then you don't have to consider the Z direction here. I'm just not going to, because I need this problem to be a little shorter. It's already been like 20 minutes. Okay, so now we've got our forces, we've got our pulleys that we've chosen, we've got the loadings on those pulleys that we've picked. We've done step 4, which is the free body diagram. Awesome. Now we need to figure out loading. Okay, this is getting into the stress analysis portion of this, because the biggest failure condition for this shaft is going to be stress failure. So when we design it, we're going to have to make sure that it doesn't fail in stress, because of yield. We're going to need to pick a material for it. We're going to need to pick dimensions for it. We got a lot of play to go along with this. But first we're going to figure out loading. Okay, so I'm just going to use this free body diagram and figure out what these loads are. Okay, so we got, drawing this again. I don't know what the step shaft in the middle is going to be. This is FP2. This is FP1. The way we drew it was RB1Y and RB2Y. Okay, this is 7/8 of an inch, which we don't need to know. The distance from here to the center of that, this is 1/4 of an inch. That's 3/8 of an inch. That's 5/8 of an inch between these two. Okay, so that's 5/8 inch, just by the way that we have this shaft configured. Center of the bearing to center of the pulley. Ooh, shoot, I forgot to add a 1/2 inch for that bushing, which means this is now no longer that, it's 1 1/8 inch between the center of the bearing and the center of the pulley. So, okay, we also know that we have the same geometry on the other side, so again, this is 1 1/8 inch. Cool. Between these two, we know that these are 3 inches apart. And that's all the dimensions we need. Great. So we'll go ahead and sum the forces in the y direction, and that's equal to negative RB1Y minus FP1 minus FP2 minus RB2Y is equal to 0, because there's no vertical movement here on this shaft. Sweet. All of those are equal, so what we end up with is negative RB1Y minus RB2Y is equal to FP1 plus FP2. We know what FP1 and FP2 are because we picked them earlier. This is 1,700 and 1,200. This is going to equal a total amount of 1,900 pounds. Okay, then we're going to go ahead and sum the moments. The moments are going to be about the z direction, because that's the plane we're looking at when we draw this moment diagram. So the sum of the moments in the z direction are equal to, let's say we're going to take it about this point right here, okay, about RB1Y. So we'll be able to solve for RB2Y. So we got our 1 1/8 inch, 3 inches, 1 1/8 inch. So we've got 1 1/8 inch times FP1, that's a negative moment. FP1 minus, then we got 4 1/8 inch to FP2, 4 1/8 inch times FP2, and then we got 4 1/8 inch plus 1 1/8 inch to RB2Y, and the way that we have it drawn right now, it's a negative moment. So we'll just keep consistency in the way that we drew it. So this is going to go out to 5 1/4 inch times RB2Y. It's kind of small. Awesome. We know what FP1 is. We know what FP2 is. If we solve this equation, RB2Y is equal to 1 over 5 1/4 times negative 1 1/8 inch times FP1 minus 4 1/8 inch times FP2. So if I grab my calculator, which also happens to be my phone, 1.125 times 1,700. We got 4.125 times 1,200. And then we divide that by 5.25, and RB2Y, I'll write it all the way down here, RB2Y is equal to negative 1,307.1 pounds. Okay, and if we go ahead and plug this back into this equation, what we get is, this is equal to 1,307.1 pounds. We plug that back into this equation, and what we get is 2,900. We get, this is equal to 1,592.9 pounds. Okay, so now we know what all of our forces are. Awesome. Okay, once we have our loading, generally it's a good idea to now draw your moment and shear diagrams. You can also draw your torque diagrams. You can draw whatever you want. You can never diagram enough, it turns out. So we'll go ahead and draw moment and shear diagrams. So for here, my shear loading, it does go down, up. The overall, it overall wants to bend like this, which I think that is, let me just make sure before I tell you. Oop. Now you gotta watch me look at stuff. Awesome. Hold on, Kale. Doesn't this class get easier? Well, it kind of does, because I'm gonna tell you what you should do here. This ends up being, when we apply this negative forces here, here we have a negative 1,500 pounds, And this is going to be positive shear force. So we go to where this is now 7 inches along the shaft, which 7 inches is the edge of the shaft. This is in the X direction. This is the shear diagram. We start out with we start out with 0 for 7/8 of the shaft at 7/8 of an inch. Then this jumps up to 1592.9 pounds. 1592.9 goes over for 1 1/8 inch, which at 2 inches, then it drops down. So this is 2 inches along the shaft. When it drops down to 108.1 pounds negative shear. Okay, so this is negative 108.1 pounds. It then travels sideways for 3 inches until it gets to 5 inches here, in which case then it jumps up to 1307, goes over and down. And this occurs at 5 7/8 inches when it goes back down. And this is 1307.1 pounds. So there's our shear force diagram. That's interesting. Pretty fun there. Maybe not as fun as it could have been. Now we've got our shear force diagram. We're going to go ahead and do our moment load diagram. Okay, so here the integral of this is 0. We know we don't have a residual moment at 0 or at 7 inches, so we're expecting the moment load at both of those points to be 0. So when we do our integrals, we know that's 0, we know that's 0, and it's got to be that way. Here we have a positive load that starts at 7/8 inches, goes here. We have a negative load that then slightly goes down like this, and then we get a positive load that once again goes like that. Okay, that's what our moment load diagram is going to look like. Our two peak moments are going to be here and here. This moment occurs right at this pulley where we have 1 1/8 inch transfer. Well, we have 1592.9 pounds transferred over 1 1/8 inch. So at that point, 1592.9 times 1.125, this moment, this positive moment, is equal to 1792.0 pound inches. Okay, this negative moment, it represents 1307.1 transfer over 1 1/8 inch. So 1307.1 times 1.125. This is equal to negative 1470.5 pound inches. That's a period. I'm just going to go ahead and erase that. Okay, so now that we have our moment and shear force figured out, awesome. We now know where our maximum moment occurs. We know where our maximum shear force occurs. We know that our torsion occurs across the entire interface. Great. So what do we do now? Well, we can sit down and we can figure out dimensions. We can go ahead and we can try doing all of this by hand. But this is not the world's greatest idea. What we're going to do instead is figure out what fatigue is going to look like here. Okay, so we figured out what loading is. Now let's look at fatigue conditions. At this location on the shaft, which is right here, what we have for our cross section is, you could have a solid cross section. If you want to save money, you could go with a hollow cross section, but do remember, well, and it would save on weight, but do remember that if you're machining a shaft and you're doing a hollow cross-section, your hollow cross-section has to be consistent for the entire shaft. You can't assume that this is going to be wider just because the step is bigger. There's no way to machine that. So you'd have, if you did a hollow cross-section, be all the way across. Since this is only a 7-inch shaft, there's not a whole lot of benefit to making this hollow. So we might as well make it solid. That does save on calculations. Okay, so we're going to assume this is a solid shaft now with some kind of a step in the middle. The greatest moment load is found right here at the pulley, but then we have that moment load being carried across that stepped shaft. And we have that torsion being carried across that stepped shaft. So I'm going to go ahead and say that the critical locations for this are going to be here and here. And it really doesn't matter what we're going to do for the step shaft. We can only make it maybe a 1/2 inch larger and have that step just be kind of a placeholder for our pulley to butt up against. So we're going to go ahead and say, you know what? Because the critical conditions occur right at the pulleys, it doesn't matter what our step is. It's going to be 1/2 inch. This is going to be a 1/2 inch, so we'll have a 1 inch. No, we'll make it a 1/4 inch. That way it's only a 1/2 inch larger at that size. It'll save us on machining when we go to machine this piece to have a smaller step. But now we got to figure out what is the diameter of that shaft right there at that critical location. We got these two critical locations. We're looking mostly at this one because this one has a higher loading. At that location, we know that the maximum stresses occur at, let's see, it's in the Y plane, it occurs here and here on that shaft, okay? So if this is the Z, Y, it occurs at the maximum Y and the minimum Y of that shaft, okay? This is your sigma bend max locations, okay? For shear actually has a maximum in the middle. We're going to go ahead and assume that the maximum shear is everywhere. The shear loading is carried like this across the face. We'll assume that the shear loading is maximum at the top and bottom too. You also have torsion. Torsion is exerting a stress like this. It will be a maximum at the top and bottom of the shaft as well. So we got the shear being at a maximum, we got the bending at a maximum. Clearly, this location at the top and bottom of the shaft are going to be the largest stress locations. Okay, that's good to know. When we have this loading, we only have one source of x directional stress. Okay, so we have sigma bend is equal to a sigma x. We got our sigma shear, because again, I'm just going through the loading conditions and what kind of cause they are. This is going to be a sigma x. It's on the x face in the y direction, so it's not a sigma, it's a tau. Tau xy. And at the top and bottom here, this is pointing in the z direction. So our stress that's caused by torsion is going to be equal to tau xz. Now this isn't necessarily a planar condition, but we'll play with it anyways. Okay. One of the nice things about this is that shear stresses, these tend to be significantly smaller than the torsional stresses. So usually you can ignore the shear load stresses because they don't create as much stress as bending or torsion. Both of these tend to be a lot larger. So for this case, to simplify the problem, I'm going to go ahead and ignore the shear stress that's due to shear loading. And we're only going to consider bending and torsion. This is going to create a planar stress condition for us, which is okay. It's not a problem. So, I mean, it actually technically already is a planar stress condition because you can rotate your axis, and these two shear stresses combine into one shear stress. But I don't like the math there. This math is a lot simpler. Ignoring the shear stress because it is, you know, it's going to be smaller than the bending stress and the torsion stress, isn't a huge problem at this step because we're not going to be doing this calculation by hand. Now, because we only have one sigma stress and we do have this shear stress, this is going to experience fully reversed loading. What we want to know is we're going to need to know what the von Mises stress at this location is. Okay, what is the von Mises stress? Why do we need to know the von Mises stress? Because the von Mises stress gives us a good image of what's going on. Okay, so fatigue conditions, our next step is we need to know what the von Mises stress is at that location. Use SolidWorks. SolidWorks, you do the stress analysis for this component, you put in these 4 loading conditions, apply a torque between these 2 places. That's it. You find the von Mises stress at this spot and at this spot. You look at the maximum on the diagram, we're good to go. Now, in order to do this, in order to plug this into SolidWorks, you're going to have to assume diameters. Okay? And you'll get a stress value out. You'll get a von Mises stress. And since this is fully reversed loading, because we only have one sigma x value, then your sigma A, when you go to do fatigue analysis, sigma A is equal to your von Mises stress, and sigma m is equal to 0. That is the most severe loading conditions that we can put onto this. But when you calculate your von Mises stress based on whatever conditions you get out of SolidWorks, you plug it right into this equation. You will then, after this step, need to pick a material. The book recommends using cold drawn steel for shafts because they do tend to have a higher yield strength. It's just typically a lot stronger in that direction. But you pick a material. Once you've picked a material, then you calculate your SE value because you're using steel. And then once you know SE, this is where you plug it into your fatigue failure criteria and you figure out your factor of safety. If your factor of safety is less than 1, your design will fail. If it's greater than 1, your design is expected under these loading conditions to succeed. For a shaft, I would expect your factor of safety should be 2. And you should aim for 2. So you may need to go back from this step, you may need to go back here, draw a different geometry for your shaft, find a different von Mises stress, same loading conditions, pick a material, which you already should have done, and then calculate your N value. So you do kind of iterate a little bit to get the optimum shaft diameter here. You do not want to have an N value close to 12. That's a bad. It shouldn't be 10 or above. I want you to try to aim for 2. If you can get an N value of 2 or really close to 2, it shows that you went through the proper design process. Okay? If you have any questions about this, we can talk about it next week in class. Next week we're going to be covering different material, but yeah, that's all that I have for shaft design. That's an example. Again, I reiterate, make SolidWorks do the math for you. We had to do a lot of setup work in order to get to this point, but actually physically calculating the stresses, since we know what von Mises stress is now, use SolidWorks. There's no reason not to. All right. That's the last lecture for this week. I'll see you on Monday.